Welcome, everybody. Today, we're going to talk about how to deploy MongoDB clusters with Terraform and Ansible just by pushing a button. Okay. Reality is a bit more than that, but still, it's going to be way simpler than the manual approach of provisioning every resource by hand and making sure all the pieces fit together, right? Which can be time-consuming and also it can be prone to errors. This is the agenda for today. We're going to start by covering some basics about Terraform. For those of you who are not familiar with it, we are going to be using Google Cloud Platform to provision all of the resources that we need for this talk. And we're also going to give you a brief introduction to Ansible. And next, we're going to go through the implementation. Hopefully, this will give you some ideas that you can take back and then apply in your own deployments. At the end, there'll be time for questions, but feel free to start typing them now if you want, if you have it, okay? I am a database architect at Percona. I work in the consulting team, and I am based in Argentina, South America. Let's do, first of all, a quick recap about how MongoDB works with sharding, okay? Basically, our application will connect to the MongoDB cluster via the MongoS process, which is like a router, okay? So basically, the MongoS will query the information that is in the config servers to figure out to which shard or shards to send the queries that it receives from the client, okay? The MongoS is also in charge of consolidating data from multiple shards when we have a scatter-gather type of query, and then sending the result over to the client. The config servers, they store the metadata database, which is like the catalog of the sharded collections, and they are provisioned normally in a replica set form, which is the basic high availability unit that we have in MongoDB. Then each of the shards will store a subset of the actual data. And also each shard is a replica set on its own, okay? Also for redundancy purposes, as well as read scaling. The target infrastructure in Google Cloud Platform will look like this. We'll have our clients go through a proxy layer that will be the MongoS processes, which we will provision in a couple of servers for redundancy. And then we will have a cluster that will consist of one or more shards. And each of them will be a 3-node replica set. Ideally, you will split this between multiple availability zones for disaster recovery and high availability, okay? As we said, the config server replica set will store the shard metadata. And all of these instances that are going to be hosting the config servers and the shards will require a persistent disk, okay, to store the database files. For the monitoring part, we're going to use a PMM server, which will require a dedicated instance. We'll talk a bit about this. And for the backup, we're going to store snapshots in Google Cloud Storage bucket, okay? For this, we will use Percona PVM. So first of all, we need to define the topology. I mean, we have a look at how it looks overall, but how many servers we want, how many availability zones, and so on. Then we're going to provision all of this using Terraform. So we need to create the instances, the disk, configure the network, and so on. And then once the infrastructure is ready, we're going to rely on Ansible to handle the software provisioning part. That means installing MongoDB, but also configuring monitoring and the backup solutions. So let's talk about Terraform a little bit. Terraform is a tool that allows you to build the infrastructure as if it was an application in GitHub, okay? So this includes low-level components like instances or storage, networking, and so on, but also higher-level things like DNS, for example. It's an open source product. There's an enterprise edition that has some additional features, but it's the core software is open source. It can work on multiple different resources. Like in this case, we're gonna discuss GCP, but it also works in Amazon or Azure and others, okay? And the idea of Terraform is that you specify the resources that make up your infrastructure by using a declarative language, and then Terraform will make sure that your actual infrastructure converges to this desired state by either adding, dropping, or modifying things, okay? The syntax is based in a HashiCorp configuration language, which looks a bit like JSON, okay? The language syntax is built around two basic constructs, which are the arguments and the blocks. The argument is quite straightforward. It's based, used to assign a value to a particular name. And then we have the blocks, which are containers for other type of content. Each of the blocks, we will declare for to create one resource, for example, a compute instance. And each block has a type, and then can have multiple labels, or it may have none at all, okay? So for this particular example that we have in the slide, we have the resource that expects two labels, okay, which is the Google Compute instance and a name. And then after the block type and the labels, the body is delimited by the curly braces, okay? And within each body, we can also nest more blocks, okay? So you can create a hierarchy. We're going to talk about how to define variables first. Input variables are the basics for customizing the behavior without editing the source code. Basically, the label after the variable word is the name, okay? And this must be unique among all the variables that share the same module. And then you can call these variables from other parts of the code, okay? And also you can define for each of these a description argument that is optional, but it can be helpful to document what you're trying to do with these variables, okay? You can also set default values, and those require literal value, okay? So let's dig into some examples of code provisioning. This is how you can provision a server with a persistent disk in GCP. We have two blocks, as you can see here. The first one calls a disk that is called CFG_disk. And we have to specify what is the name, okay, of the disk in the GCP resource. Also, we can reference some variables, for example, to define what is the type and what is the size. And then also we need to define on which zone we want the disk. The second block creates a compute instance with a specific AMI and also attaches the disk that we create, okay? In this case, CFG is the name of the instance. And you can see how we can reference the variables from this piece of code by prefixing them with a var dot prefix. Also, there are some built-in functions that we can call. For example, lookup function is useful to retrieve elements from a map, okay? So we specify the key and it will give us, in this case, the correct AMI by specifying the region. And if the given key does not exist, then the default value will be returned in this case. Also, we can see some examples of what a nested block looks like. So for example, here to attach the disk that we created, we are using a nested block and then another one to specify the network properties of the instance, okay? These are the basic commands to work with Terraform. First, we have the init command, which is used to initialize a directory. And this is the first thing that we do when we are cloning a Terraform repository, for example, from version control. And also one of the steps that happens here is that the different plugins are downloaded. So if you're going to be interacting with one of the cloud providers, you will need Terraform to download the plugin, and that will happen when you do the init. The Terraform plan will present a description of the changes that will be performed, so you have a chance to review what will happen when you run the next step, which is the Terraform apply. Okay. If you just run the apply, it will also show the plan first, and then ask you for confirmation to actually run and make the changes. Okay. And finally, we have the Terraform destroy, which basically tears down all of the resources that are managed by the current directory. Okay. And also this command will ask you for confirmation before it does any changes, so it's safe to run to see what will happen. This is a very simple example of how it looks like when you're handling a storage bucket. We need to specify the properties of the bucket we want, and then Terraform will go ahead and check what we have in our infrastructure and figure out what changes are required to make the infrastructure again converge to what we want. If there is a new resource to be created, then the plus sign, and there will also be a green color indicating this very clearly. And if there's anything that will be removed as a consequence of our actions, then that will be marked with a minus sign and also in red in the code, okay? So normally what happens is that Terraform will try to modify existing resources, but if there's something that we specify that we want changed, but it cannot be changed dynamically, let's say, it will be like the resource will be dropped and then created from scratch, okay? But always you get a prompt about the steps. So you have a chance to confirm before anything happens. So going back to our goal of creating our infrastructure for MongoDB, we need to think about what we need in terms of Terraform resources, okay? So a MongoDB server is basically an instance plus persisting disk, except for the MongoS routers, we do not need any persistence. Also, we're going to need some firewall rules, okay, to allow the communication between the instances and inside and outside them. And then maybe we need some init scripts to do the basic setup, like mounting the volume and doing some basic OS level tuning, okay? For example, one of the things that we normally do for MongoDB is disable the transparent huge pages. One possible way to achieve this is to create separate files for each of the components, okay? Different files for Terraform, for the MongoS router, for each of the shard, the config server, and whatever else we need, okay? It's a good idea to keep our variables in a separate file so we can customize our deployment without altering the source code every time. In addition to the servers and variables, we can create separate files for the network infrastructure, for example, where we will define things like the VPC, the subnets, so on. And also for the backup part, maybe all the things that we need to take a backup, we can put in a single file, like creating of the cloud storage bucket, the roles and the service accounts that we need, and maybe even some lifecycle roles can go there, okay? So let's look at these tasks in a bit more detail. To configure the network, we have to define a region, then create a VPC, and then subnets within it, okay? So for this, we can use data sources, which are a part of Terraform that allows us to interact with resources that are outside of Terraform itself, okay? So for this case, the provider will expose what are the availability zones that we have with capacity to create instances, and we can define this dynamically by using this provider, okay? And query what of the zones are up, and then based on this, we can create our resources, okay? Next, we can create a VPC using the block in the middle and give it a name that we can later reference within the code. And we can also use the Google Compute Subnetwork resource to create the subnets that we are going to use. And as you can see here, we are referencing the VPC ID that comes from the previous block, okay? That's created as part of the previous block. For creating the instances, we saw an example of this, but there's another trick here that might be helpful, that is to use the count argument, okay? If you put this within a block, it will create several copies of the resource. And then it will also give us a count.index argument that we can reference. This starts with 0, okay? And so we can use this by putting it through the modulo operator to split our instances between, for example, 3 availability zones that have capacity, okay? This is how it works. So again, this will give us the instances split for high availability within zones. For the network access, each network will have its own firewall to control what can happen between the instances. And so to handle what ports we need, we can create a resource and then use some target tags for the instances, okay? For this particular case, we can allow SSH access to manage the instances, and also we want communications to happen over the MongoDB port. So we can define that in the allow list. And again, the target tags will be marked in the instances to see which of the instances will the firewall rules apply, okay? So any instance that is marked with MongoDB CFG will be using these firewall rules, okay? And we can do the same for the other components. For the backup infrastructure, first we need a place to store the backup, so we can create a cloud storage bucket for this. And also we need to make sure that the instances that will be part of our deployment will be able to interact with this bucket. So we need to manage that. And also we could do things like control the life cycle of the objects in the bucket. So if, for example, our backup process fails to remove some older backups for whatever reason, we also have the bucket itself that will be removing any old data. The steps to create all of these will be different depending on the cloud provider. For the case of GCP, we have the storage bucket that instances will be able to read and write. Then instances will assume a role via a service account, okay, to do this. So we need to create the service account for the backup service. And then we need to create an HMAC key pair that is tied to the service account. And then we need to assign also a proper role for the service account. For example, we can give storage admin, which will have the required privileges, so that instances will assume the role through the service account and then be able to interact with the bucket itself, okay? And this is all the code that we need for what I described. First, we define the bucket with the name and the region. Then we create the service account for the backup service. Then we create the HMAC key pair for the service account. And finally, we modify the bucket policy to give the storage admin role, okay, to the service account. For the monitoring part, we can use Percona monitoring and management, which is called PMM. And this consists of a client component that runs locally on each of the instances, collecting the metrics via different exporters, and then we'll push them over to the dedicated server, okay? The PMM server is running Grafana for visualization and metrics history. And also it has query analytics functionalities, so you can see the slow queries in almost real time. And you can also configure things like alerts and send them via email, PagerDuty, or Slack, for example, through a webhook. And there is also functionality to use to trigger the backups from there, okay? There is a demo available in case you want to see how it looks like in this link. So at this point, we covered how to provision the different parts, but now we have to deal with the software installation, okay? So let's see how we do this. As I said before, we're going to be using Ansible for this. And Ansible is, first of all, an automation engine You can use it for provisioning software, configuration management, things like that. And it will use SSH to connect to the host and apply the change. So there are no agents involved. It's open source. Also, it was acquired by Red Hat back in 2015, I think. But it's still open source, although there's a paid option. And there's also a web interface that is called AWS, in case you're interested. The benefits that Ansible has over other tools like Chef or Puppet, for example, is that there is no agent involved, okay? So you install Ansible on a control machine, which could even be your laptop. And then SSH connectivity is all you need. Okay? There are no firewall rules or agent. The only requirement it has is Python, but that already is installed by default in most of the Linux distributions nowadays. The syntax is YAML, okay? So this is standard format that once you get the hang of it, it's quite straightforward to work with. And by default, it's secure since, again, it's all it needs the SSH port open. So in Ansible, we have this concept of the control machine, like I was saying, which is the place where you run the code from, which can be, again, your laptop or a designated server. And it's only needed, like this control machine, it's only needed when you want to run the code. You'll need to keep it around afterwards if you don't want to, okay? There's no further communication between the machine and the rest of your servers after you run the code. The managed nodes or the targets are the hosts that Ansible will work against to make the changes, okay? There are two options for the Ansible inventory. The easiest one is to work with a static inventory, which you maintain manually, and it's basically a list of groups and hosts, okay, which can be in text or YAML format. And if you have a small deployment or your hosts don't change very often, this is normally what you use. There's also the possibility of using a dynamic inventory, which can integrate with the different cloud providers. Or you can write your own plugin, okay, as well. The default location of the inventory file for Ansible is in etc Ansible hosts. This is an example of how a static inventory looks like. As I mentioned, you can put the different hosts in one or more groups. For example, an instance could be both a web server and a database server in this example. The group names go between the brackets, as you can see. And if you have hosts with a similar naming pattern, you can add them as a range rather than listing each of the hosts individually. And also, you can assign variables to individual hosts or groups, and you can then reference those variables within your Ansible code. The Ansible modules are built-in pieces of code that you can use to accomplish the different tasks in Ansible. And the idea is they provide an interface that you can use to abstract yourself from the task and to focus instead on the outcome, okay? So you let the module handle all the details of the implementation, and you just focus on the high-level steps, okay? The modules are the building blocks for the playbooks, which we will see next. And a key concept is that they are designed to be idempotent, which means if you run a module multiple times, you should always get to the same end state, no matter what was the initial state, okay? There are many modules available for different tasks, so that each time that you need to do something, check if there's already a module available for that, rather than writing your own code, okay? And you have here some examples of how to call a module. For example, the ping module is handy when you want to test communication between the Ansible software and some of the servers, okay? And this is how you can run it and the output that will be returned. Like I said, in order to do things that are more complete, we need a way to combine the modules, and that is where the playbooks come into play. The playbooks basically are composed of one or more plays in Ansible terms that are pieces of code that will be run against a particular server. And each of these plays contains a number of tasks, okay? So a task can be, for example, calling a built-in module. And the playbooks are written in YAML format like all the Ansible code. Here is an example of a simple inventory file that we're going to use for the purpose of our talk. So let's pretend we have two different groups with 10 servers each. One of the groups is for the web servers and the other for database servers. And note that I am using here the range notation to avoid putting all of the servers in a list. Okay. And here is what a playbook looks like for this inventory file. Indentation is super important. If you don't indent properly, the playbook will give an error. And we have here two plays, okay? The first one is applying to the web service group, and it has two tasks. One is to make sure that Apache is installed at the latest version. And the other one is to make sure that the service is actually started. And the second play is just applied to the databases group. And it just has one task that is to call the YAM module and ensure that the Postgres version is the latest one available. Okay. For specific plays within the playbook, we have to define, again, to which host it applies to. So the host specification has to match with the groups in the inventory file. And you will see that you can also use wildcards here. And each of the tasks, again, will perform an operation. The most simple one is to call a built-in module with some parameters, but we can do some other things as well, okay? To run the playbook, we use the Ansible playbook command, and you have to specify a host pattern, then the playbook name. In this case, we're doing O as the host pattern. And after the playbook name, you can further refine which of the hosts will be run against by using the limit option. So the host pattern is the first filter, and then you can further limit within a host pattern with the limit argument, okay? This is how the output looks like. It will basically show the output of each of the tasks for each of the hosts. So if it says OK, it means that no work had to be done, as the state of the host was already matching the desired state that we specified in the task. So for example, if we said that a service had to be started, that means that when Ansible ran, the service was already started. Then if it says changed, it means that Ansible had to do something to make it comply with the desired state. So for example, if we say the service was supposed to be started, maybe the service was stopped and Ansible had to start, okay? And also at the end, there is a recap with a per host summary that says how many of these different things Ansible had to do. The case of variables for Ansible is similar to what we saw for Terraform. There are different types of variables. There are simple ones that combine a name with a specific value. Then we can also have a list variable, for example, like this, where we specify each of the members. And then we can also have dictionary, which is basically key value pairs, okay, used to store related data. So we will use this as part of the code. So let's see how we can automate the MongoDB deployment using Ansible. The high-level steps will be, first of all, as with any Ansible code, we have to define the inventory file. And as we saw, the structure of this file will be quite important because it will be closely related to the code that we will be writing. Then, in order to make the code reusable, always a good practice to put the variables outside, okay? So for things like the number of shards, we can parameterize that. And the final step, of course, will be running the Ansible playbook command to actually execute the code. So let's talk a bit about the inventory file for the MongoDB first. For a sharded cluster, we will define a specific structure that is going to be helpful. And this will be to create one group per shard and to name those groups with the shard word at the beginning. So we'll create shard 1, shard 2, and so on. Then we'll have a specific group for the config servers that will be called CFG. And then different group for the routers, okay, the MongoOS processes. And we will define the name of this group as MongoOS, so we can easily reference this from our code. Here's an example of how it would look like, okay? In this case, we have two shards, where each of the shards is a 3-node replica set, as we saw. And also we will have a 3-node replica set for the config server. And you might notice here we have a specific type that is called MongoDB primary, which we will apply this to a random server in each of the groups. And we will then use this to arbitrarily define what is going to be the primary server when we bootstrap the replica set. So this will make the code easier, as you don't need to figure out at runtime which server is going to be the primary. Otherwise, when you run the initialize command for the replica set, any of the 3 servers by default will be chosen, okay? And if you have, for example, multiple environments, you could keep multiple inventory files. For example, one for dev, one for test, and one for prod. And that would be the way you could reuse this for multiple environments. The inventory file, in this case, we generated manually, but we could also generate it from Terraform. There is the local file resource that helps us write to a file in the host OS from Terraform. So we could use some templates to dynamically create the host automatically, okay, as part of our Terraform run. We're not going to cover all the details because it would make the presentation too large, but you can refer to this blog post that I'm linking here for more details if you're interested in this. So let's talk a bit about the variables file. And remember that this file will contain all the user modifiable parameters. And it looks pretty much like this, okay? Of course, this is an extract only, but the idea is you'll have all the different variables and with structures that we saw, like, for example, the simple variables or the dictionaries, okay? And the idea is we're going to define things here, like, for example, what is the source of the files, if we're going to copy them over from somewhere, or we're going to install them from a repository. We could also define the package names or the paths that we're going to be using. What are the ports that MongoDB will be using? What is the location for the MongoDB data, the logs, and so on? What's the authentication mechanism, the encryption configuration, and also the things for the backup, like what is the storage bucket, and what is the frequency of the backup. So all of these we could control from the variables file. So basically, the things that we need to do can be summarized in all of these tasks, okay? We're going to need a task to install packages. We're going to need to create config files dynamically. We need to control processes, start and stop them. Also, in terms of MongoDB, we need to initialize the replica set. We need to create users within MongoDB and also configure the backup job. We're going to need to register our host with the monitoring. And also, we're going to need to add the shards to the MongoDB cluster when we have them configured, okay? So let's see how we can do all of these tasks using Ansible on a high level. To install a package, it's quite straightforward. There is a built-in module which we can use, and we can loop through a list of packages using this construct that is called with items, okay? The packages between the double curly braces is a dynamic variable in this case, and it will basically allow us to iterate through all of the package list and feed them to the package module. That is the one that will be making sure that the package is installed. Okay. Again, the item within the package module will be calculated dynamically based on our variable in this case. For configuration files, we ideally want to generate them dynamically. We want to be able to include or exclude specific sections depending on what kind of cluster we want. We could want a cluster with a config file, with a key file authentication, or maybe there's another cluster that needs certificates instead. And of course, there are other different conditional things. So basically, variables are not enough in this case. We want to use Ansible templates, which is the solution to create dynamic content with Ansible. So let's see how this works. The templates are built in, okay? And they have this specific job of creating files with dynamic content. They use Jinja 2 engine, which is a templating engine that is developed in Python. And when we are writing Ansible code, normally the templates, we can put them in a template subdirectory to keep them separate from the rest of the code, okay? This is an example of how to create a config file that is templated. Basically, within the templates, we can use conditionals like if then else blocks, for example, for the purpose that I described, which is to decide whether this particular MongoDB cluster will use certificate-based authentication or key file, okay? So basically, we can define a variable that says use TLS, for example, and then say yes or no. And based on the value of this, we can include specific sections in the MongoDB configuration file. And then once we have that, the other part is to use the template module, okay? And this is the actual part of the Ansible that will render the template file by replacing all of the conditionals and then copy that over to the destination host. And then it will give the destination file the proper permissions and the owner and group, okay? So it has three parts. We have the template file, then the variables file, and the task that will render the template in place. Next, to start or stop a process, we saw this is very simple with the service module. One caveat here is that normally these things have to happen with the root credentials. So there is a become directive in Ansible that basically tells Ansible to sudo before running this particular task. So it gets handy for this particular piece of code, okay? Before discussing how to initialize the replica set, that, as you know, it's done with the rs.initiate command, let's review our inventory file one more time. Here I highlighted a few things that I wanted to mention because it will become handy for the initialization later. And remember that we have decided that each group will have the name of the shard, okay, and the list of servers, and whether it's a config file or a shard. So at runtime, Ansible will create a group names array that will contain the list of groups that each host will belong to, okay? So for example, for host 1, which is the first host in our inventory file, this group names array will have the CFG value, okay, which is the group where it belongs to. So remembering that, we can initialize the replica set by using a template like this, which looks quite complicated, but if we start dissecting it, it's not that complex, okay? Basically, we can use this group names array to figure out the name of the replica set by picking the first group that a host appears in. Okay, so going back to the last slide, for example, for source 1, remember that CFG is the group, okay? So the ID in this case will be CFG. And then we can use also the groups variable, and that will be listing all of the hosts that are part of the first group in this case, okay? So we can say groups and then give the name of the first group, and that will list all of the hosts that are members of this group. And we can also build the different members by iterating using this for loop, okay? And then also there is a comma separated list that we need to generate. And for this, it is useful to have this variable that Ansible gives us, that is the ability to get the index of each of the elements within a loop, okay? So basically, if we are at the last element of the loop, we can avoid putting the comma, and if not, we can simply put the comma to generate it properly. And here is what it looks like when you replace this, okay? Just for the first host to avoid printing too much, but it will be generated like this, okay? Then once the template file is ready, we can simply call the template module to render it again and put it in place. And in this case, it will put in the TMP directory, because we really don't need it for any other purpose than bootstrapping the replica set. And here is where the MongoDB primary tag that we defined earlier comes in handy, because it will help us to run the initiate command just once in the server that is defined like that. To create the users, we can also use templates. That way, we don't need to hard code any privileges. And the roles list, it could also be generated dynamically. In this case, we have a fixed list of roles for the different groups that are required for the monitoring user. And then again, we call the template to render it in place and then run it through the Mongo shell to create the user, okay? To configure the backup, we have a module that is handy to create a cron job. Basically, this will create a file under the cron directory that runs at the specific time. And in this case, we are calling the PVM product that is the one that will be taking our backups. To configure the monitoring, we need to run a few commands for PMM, and we can easily do it with the shell module, replacing the different variables that we have, for example, for things like the credentials. And all of these also run as root, so we have to say become true for this particular part.
Hi, Yvonne, let me just stop for 1 second and say we're scheduled to end at 12:15, but there's no one after you in this room, so I'm sure it's okay to go a little over. Just wanted to let you know.
Thank you very much. The last part, we generate the add shard command and run it on a MongoS. And the idea for this is that we can dynamically generate the command, again, using the variables that we have. And then there's a way to run this on the MongoS server instead of in the actual shard by doing the delegate to, okay? So delegating to the first member of the MongoS, it will do the trick. And all that's left now is to run the playbook to deploy the cluster with the Ansible playbook command, and we can feed it with the root password, and your cluster will be ready to roll. So let's recap the steps we took. We defined the topology, we created the infrastructure with Ansible, with Terraform, and then we generated the inventory file for Ansible and ran Ansible to install the software. So in terms of actual steps, we had to edit the variables for both Ansible and Terraform to define the infrastructure. Those are like the blueprints. Then we run the Terraform apply command. And finally, the Ansible playbook to take care of all the software provision. This approach has several benefits. We define a streamlined approach. We reduce the human error. And we make sure that all of the resources that we create will be done in the same way. And all of them will be monitored, and backed up as well, okay, out of the box. That's all. Thank you for attending.